Chemical Reaction Engineering Project. Final presentation. We are going to talk about the process of catalytic reforming of naphtha. Why? Petroleum is a valuable product, a fossil fuel that takes millions of years to form beneath the Earth's surface from the decomposition of living organisms. Petroleum is a mixture of hydrocarbons that can be separated into different components, such as natural gas, gasoline, naphtha, among many others. One of the most used products is gasoline, which needs a certain octane level to work as a fuel. Because of its importance for society, we have decided to talk about this process. Nowadays, almost every refinery in the world has a reformer, with the purpose of increasing the octane rating in gasoline.
The purpose of a gasoline reformer is to improve the octane rating for gasoline. Octanes determine the way combustion of gasoline in the engine cylinder. At higher octane, the combustion generated in the cylinder is more uniform and controlled. On the contrary, at lower octane, the fuel detonates and explodes in the engine. A higher octane ensures a more efficient use of a fuel, understood as the best possible use of energy that releases its combustion to propel the car. For years, UOP has been a leader providing of reforming solutions that meet customer needs for high octane and low sulfur gasoline. They produce more than a dozen different high-performance reforming catalysts for the production of high-octane gasoline or aromatics. For this reforming process, the octane rating is increased to gasolines by means of different types of reaction occurring in the process. It is worth mentioning that in this process, the production contains reformed gasoline and LPG light gases.
Now, let's talk about the fundamental reactions that occur during the process. The process converts low-octane linear hydrocarbons, also known as paraffins, into cyclic naphthene and branched alkanes, also known as isoparaffins, which are then partially dehydrogenated to produce high-octane aromatic hydrocarbons. All of this using platinum as a catalyst. Without the use of a catalyst, the reaction won't be able to occur. Here, we can see an example of dehydrogenation reaction taking place, followed by an isomerization reaction. This reaction occurs in our process too, but it doesn't necessarily affect the products. Let's talk a little more about the dehydration reaction, which we can see in the image below. The activation energy for this reaction is actually very high. That's why we need to use platinum as a catalyst in order to diminish the activation energy and for the reaction to occur. When the reaction occurs, then we will be able to extract those hydrogens. After extracting the hydrogens, the molecule forms double bonds. And as we see in the image, we obtain 3 free hydrogens, which are a secondary product of our process, while the main product is already formed. Let's make the analysis to decide which type of reactor is the best one to be used in the reaction process. First of all, with the experimental data that we have obtained based on the research we have done, we can see in the result how the concentration of reactants and products vary with time. We can also observe what happens when we keep some of the reaction-involved parts constant, the products or the reactants. With this information, we can conclude, based on the experimental data analysis, that we have a second-order reaction. Now, let's make an stoichiometric table to represent the data obtained in the previous analysis. As we can see in the next table, when we are at the time 0, the concentration of the reactants is 0.7002 moles per liter, and both of our products are non-existent, which means we have a zero concentration. After a determined time called time t equal t, we observe how the reactant concentration has diminished and the product concentrations have increased. Not necessarily in the same amount, but we have both of the products present. The next step is having to make a decision based on our previous analysis and the research we have done. We can say the ideal reactor to achieve a higher conversion of this process is a packed bed reactor, also known as a PBR. This reactor is well known to be an excellent option when we have to use catalyst. That's why we choose it. But it doesn't mean that we can only use it as it is. In order to reduce the cost and waste of our process, we can implement a reflux. This with the objective to get more benefits from the catalyst by removing the carbon and getting it to the beginning of the process again. This will make the percentage of conversion get higher. Last but not least, we have to define the parameters of our reaction. The flow rate that we're going to be using are 25,000 barrels per day of a 56% octane desulfurized gasoline. This will be useful to produce 19,000 barrels per day of a 99% reformed gasoline, 4,000 barrels per day of dry gas, and the rest of liquid purified gas, which will be used to get energy from it as it is one of our secondary products. The heating requirement is high temperature. We have estimated an approximately 500 degrees Celsius. Pressure is about 12.5 kilograms per square centimeter. This is equivalent to 13 absolute atmospheres.
Calculations. In the calculations, our assumptions were that the flow rate at the exit of the reactor is only benzene, the flow rate at the entry of the reactor is only cyclohexane. We assume a basis of a volumetric flow rate of 1 cubic meter per second. The density of catalyst is only for platinum because we have a mixed catalyst. And we assume a 1 barrel per day is equal to 0.159 cubic meters. Then we first in the calculations we calculate the molar flow rate with the density of the benzene, and then we obtain the initial concentration with the formula of the concentration and conversion. In order to calculate the volume, we use the formula of the PBR. The catalyzed weight and reactor volume are related by the catalyzed bulk density. Then we assume that the mass of catalytes is equal to the volume, and we use the next formulas. We calculate the mass of catalyzed, and then with the density of the platinum, we obtain the volume of the catalyst, and it is equal to the volume of the reactor. And we obtain a volume of 642.8 liters. And the analysis of our results are our results make sense, 0.35 cubic meters per second, but we don't know the correct value of the volumetric flow rate as we assumed. As it is a big production, we don't really know how much will be needed in order to obtain this value. The density used for the catalyst was only for platinum due to the lack of information of all the catalyzed. Then in the entry we assume only cyclohexane, but we know that it is a mixture of naphtha, and there is limited date in order to calculate values for the reaction rate of the catalyzed in a non-elementary reaction.
A complete naphtha reforming plant has an approximate investment cost of $500 million, without considering the operation and maintenance costs of the plant, in addition to which the production variables of the plant have to be considered, since the more products of quality produced and the demand for high-quality naphthas remain constant, the total process of the plant will remain profitable. It is important to consider the plant's reliability due to the fact that a new catalyst load has an approximate price of $5 million for a normal operating load, in addition to the price per reforming reactor alone of $100 million. The demand for high-octane gasoline ranges between more than 1,000,000 barrels per day. Therefore, 5 million pesos per day would be obtained.
In conclusion of this project, we can perform a green analysis in order to diminish the amount of greenhouse gases produced in the transportation of the materials. Most of the products can be recirculated because the catalyst enters to reflux where the active catalyst is recovered to have less economic and loss generation of gases. Also, the additional hydrogen formation by the catalytic reactor is recovered and put to use in subsequent reforming in other processes through the refinery. In addition to the other products of reforming are light gases and high-octane gasoline blending component, called reformate. We have a very important residue in the industry that is hydrogen sulfide, which has a great importance in the industry and can be stored and sold as new resource of monetary incomes. Thanks to the technology that we use as energy source in the industrial plant, the production will be considered as green facility. The use of natural gas as fuel has many advantages over electricity or diesel, such as lower price and its low environmental impact. Respect in the reforming in the whole, we can say the catalytic reforming process is one of the most important processes in the petroleum and petrochemical industries, which produce a high octane number of gasoline. In this aspect, obtaining a product with a higher octane is utmost importance in almost any industry, since it determines a higher efficiency in the fuel uses and cost saving either by using less fuel and great power.